This is a recording of the first half of the 6.3 section. This particular recording will focus on binomial random variables. We've had a discussion that random variables are things that are both unpredictable in the short term and they produce numbers. Binomial random variables are a particular subset of discrete random variables that meet the binomial setting. The binomial setting has to meet these four criteria. For every single trial that we have, it's a series of trials, um, there's only two possible outcomes, which we will generally classify as success or failure. Each trial needs to be independent, meaning that earlier trials have no effect on future trials. There is a set number of trials, and then the probability of success on each trial is the same. If we meet the binomial setting and we count up the number of successes in the set number of trials, we have a binomial random variable. So a binomial random variable happens when we count the number of successes in a binomial setting. The probability distribution of that variable is called a binomial distribution, and the only parameters are n and p, meaning if you tell me the number of trials and the probability of success on each trial, then we know everything there is to know about that binomial setting. Let's take a look at some situations that may or may not be binomial settings. It says roll a die 10 times and let x be the number of sixes. Well, let's see if it meets the B criteria. Do we have success or failure? Yeah, success is considered getting a six, and failure is not getting a six. So it meets the binary setting. Is every trial independent? Well, we already know that rolls of dice are indeed independent, so they're independent. Is there a set number of trials? Yeah, the set number of trials is 10 because we're going to roll a die 10 times. And S, is the probability of success the same on every trial? Well, the answer to that is yes, because the probability is 1/6. So this fits the binomial setting. Okay. Observe the next 100 cars that go by and let C, the random variable, be the color. Do we have success or failure here? So are we binary? Um, I don't know what success is in this case. In the moment we fail one of the criteria, then the answer is no, this is not binomial. Okay. C, shoot a basketball 20 times from various locations in the court and let Y be the number of shots made. Well, are we binary? Yeah. Uh, Success is making the shot, and failure is otherwise. So we meet that criteria. Is every trial independent? Well, I'm not sure we can say that every single shot that you take with a basketball is independent. You learn a little bit of every shot. But for the sake of argument for this particular problem, we're going to say yes, independent, just for the sake of argument, that later shots are not influenced by earlier shots. So we'll say yes, independent for the sake of argument. And is there a set number of trials? Yeah. N is equal to 20. Same probability? Ah, this is where we fail. No, because probabilities change based on where you are in the court, based on your location. So it fails the same probability condition and therefore not binary. All right. Binary probabilities. We know we have this random variable, and we've been discussing about how to find the probability that the random variable takes on various values. Uh, let's say each child in a, of a particular pair of parents has a 25% chance of having type O blood. Genetics say that children receive genes from their parents independently. If these parents have five children, count X the children with type O blood in this binomial variable situation. N equals 5 and probability of point of the probability of success on any individual trial is 0.25. Now, what's the probability of zero successes out of the five trials? Well, I'm going to write that down as it's essentially five failures in a row. And the probability of the first failure is 0.75 because the probability of success is 0.25. Probability of failure is 1 minus 2.5, which is 0.75. And the second and the third and the fourth and the fifth, each of them has probability 0.75 because they're all failures. So we could say that this probability is 0.75 to the fifth power. To the fifth power. Well, let's go ahead and go to desmos and let's calculate 0.75 to the fifth power, and that's about 23.7%. 0.237 is that probability. All right, that seems pretty easy to calculate. But what happens when we say there's one success? Well, one way to get one success is that you have a success and it's followed by four failures, or probability of success followed by the probability of those four failures, which I might write as 0.25 times 0.75 to the fourth. And again, I'll switch over to Desmos and we'll do that calculation. 0.725, oops, there we go. Let's clean that down. All right, 0.25 times 0.75 to the fourth, all right, which happens about 7.9% of the time. 0.790% of the time. All right, oops, 7.1, 9.1. All right, but that's not the only way to get exactly one success. You could have a failure and then follow that by a success and then three failures, in which case we might think of the probability as 0.275 times 0.25 times 0.75 times 0.75 times 0.75. Now, if you're allowed to rearrange the things that you're multiplying, you'll realize that this is the same as 0.25 times 0.75 to the fourth and shares that 0.0719 or 791 value. And it doesn't take too much more to realize that if I move that success to the third, it's still going to end up having that same probability of success. And if the success is in the fourth position, or if the success is in the last position, they all end up being the same probability. So what would we say the probability then of having exactly one success in these trials? Well, I would say it's 5 because we have 5 different ways that you might encounter one success times that probability of 0.0791. 5 times 0.0791. So about 39.55%. 0.3955. All right. I think you handled that one pretty well. Well, what about two successes? Well, this is going to be harder, isn't it? Because I might say two successes, I could get success, success, failure, failure, failure. And with its probability of 0.25 times 0.25 times 0.75 times 0.75 times 0.75, or 0.25 squared times 0.75 to the third. Okay? 0.25 squared times 0.75 to the third power, okay, 0.0264. 0.0264. Okay. And that's one way of having two successes and three failures. Well, how many other ways are there? Well, how about success, failure, success, failure, failure? How about success, failure, failure, success, failure? How about success, failure, 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 success? How about failure, success, success, failure, failure? How about failure, success, failure, success, failure? How about failure, success, failure, failure, success? How about failure, failure, success, success, failure? How about failure, failure, success, failure, success? And lastly, failure, 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 success, success. Well, there are 10 of these. So maybe we can think about the probability of having exactly two successes as 10 times this 0.0264 probability, or 26.4%. So this number 10, or the five different ways of having one success, these are referred to as the binomial coefficient. Um, the binomial coefficient is that multiplier, the 5, the 10, the 5, or in this case, the 1. There's only one way to have all failures. And this is a formula that's not testable, um, that would allow us to calculate this by hand. All right. So for example, we might call this idea that we want to find out how many different ways are there to have two successes in five trials. We might call that 5 choose 2 using this notation. Okay. This formula says that 5 choose 2 is 5 factorial, which is 5 times 2 times 5 times 4 times 3 times 2 times 1, divided by k is the bottom number, 2 factorial, and then n minus k. Now, n minus k, n is 5 and k is 2, so that's 3 factorial, 3 times 2 times 1. And then you say, well, this cancels out nicely. These 3's, these 2's, these 1's cancel. This 2 cancels with this 4 and leaves a 2, and we get the answer 10. Yep, we had 10 different ways of choosing or having two successes out of five trials. Now, there's a couple of other ways that we want to think about getting this number without doing that hard work. One of them is using Pascal's triangle. And if you've seen this before, the numbers in Pascal's triangle end up coming from these binomial coefficients. 1, 5, 10, 10, 5, 1. And these numbers are found by adding the two numbers above them. 1 plus 2 is 3, 3 plus 3 is 6, 4, 1 plus 4 is 5, 4 plus 6 is 10, etc. And the number 10 is that number right there, because we're in the fifth row, 0, 1, 2 successes. So you could read it off of Pascal's triangle. But the way that we're probably going to end up doing it mostly is that this 5 choose 2 can be found in Desmos by using a command called NCR, all right? And putting 5 comma 2 into NCR. I want you to be careful here that when we use Desmos to do this, N needs to be lowercase, C needs to be uppercase, and R needs to be lowercase. Parenthesis, and it was 5 comma 2, and there's that 10 value that we just talked about. So we can find this on Desmos using that function, right? Again, we call it the binomial coefficient. So how do we calculate the binomial probabilities in the easiest way? Well, we're going to use this formula which uses the binomial coefficient and choose k. Here is the probability of successes taken to the power of the number of successes that we had. So this is kind of like the 0.25 squared when we had two successes. 1 minus p is the probability of failure, and this is us taking the probability of failure. N minus k is the number of failures. So this probability that we just did, um, this probability of two successes in that earlier situation would have been thought of as 5 choose 2 times 0.25 squared times 0.75 cubed. And you recognize this as those individual numbers and this as the binomial coefficient 10, that 10 multiplier. All right. So, what's the probability then of having exactly three children have the type O blood type? Probability that X is equal to 3 can be simply written as 5 choose 3, 0.25 to the third, probability of success to the power of the number of successes times 0.75 squared. And we'll switch over to the calculator to calculate that. That is N capital R or capital C R 5 comma 3, close that parenthesis, multiply that by 0.25 to the third power, and we're going to multiply that by 0.75 to the second power. And we get that number 0.0879. 0.0879. Okay. Last question. Should parents be surprised if they have three or more type O children blood? Okay. Well, more than three, that would be like the probability of having exactly four children with type O blood and the probability of five children with type O blood. Well, this first one is 5 choose 4 times 0.25 to the fourth times 0.75 to the first. And the last one is 5 choose 5, 0.25 to the fifth times 0.75. And there's no successes in that last one. So let's do that quick calculation on the calculator. All right. And that would be N capital C R 5 choose 4 times 0.25 to the fourth power. And we're going to multiply that by 0.75 to the zeroth or to the first power. Now, that statement is really close to the one we'll do for the exactly 5. So I'm just going to copy and paste it. And that is 5 choose 5, 25.25 to the fifth, and 0.75 to the zeroth. Okay, and what do we get out of that calculation? We get 0.0156. 0.0156. Now, because that number is less than 5%, and 5% is our arbitrary value for being surprised, we would say, indeed, I would be surprised. Because the probability is less than 5%, I would be surprised. Now we need context that there are more than three type O blood children. All righty. Okay, check for understanding. Suppose you came into class today unprepared for a quiz. You didn't read the text, you didn't do the practice problems, you didn't take notes, and you didn't ask any questions in class. And of course, this is strictly hypothetical. The quiz consists of 10 multiple choice questions. Since you're completely unprepared, you decide to just randomly fill in the answers on the bubble sheet without even reading the questions. Let's say X is the number of questions you get right. By the way, this is our typical exam for our class, which is a 5 option um, uh, question for multiple choice. Well, what's the probability, or say, okay, we show that X is a random variable. Well, binary, yeah, because success is guessing right. I is, are we independent? Yeah, well, getting an answer correct earlier has no effect on later ones, so we're independent. Is there a set number of trials? Yeah, the number of trials is 10 because there's 10 questions. And does every trial have the same probability of success? Well, if there's 5 options per question, that means the probability of answering correct is 1/5 or zero point 0.2. So what's the probability that X is equal to 3? And what does that mean? Well, the probability that X is equal to 3 is 10 choose 3 times zero point 0.2 to the third power times zero point 0.8 to the seventh power. Again, let's switch over to the computer or to Desmos. NCR 10 choose 3. Then we'll multiply this by zero point 0.2 to the third, and we'll multiply this by zero point 0.8 to the seventh. About 20% chance, 0.2013. 2013. What does that mean? There is a 20.31% chance of guessing exactly 3 questions correctly. Okay. To get a passing score, student must correctly guess at least 6 times. Would you be surprised if you earned a passing score? Now, this would be like the probability of getting exactly 6 right, or the probability of getting exactly 7 right, or, and I could keep on going, in doing all of those. Doing those individually is really, really hard. So we are going to skip forward and look at this technology section. Now, this section is written up for the TI Inspire, but we're going to talk about how we would do similar things in Desmos. We've already found that, 5 choose 2 on Desmos would be N capital CR 5 2, for example. We've already got that down. Um, but um, in Desmos, we could also do calculations of binomial probabilities directly. We're not going to be using this stuff. Sorry, we're not going to be using the inspire commands, but we are going to say, hey, imagine we're back in the typo blood situation, and we want to find out the probability of exactly 3 successes. Here's how you would do such a thing in Desmos. All right, first of all, there's a command under the functions area, and it's way down in what's referred to as the distributions area. Probability distributions. There's our normal distribution that we played around with, but here's binomial distribution. So we're going to choose that. Now, the binomial distribution requires two parameters. How many trials? In the type O blood problem, it was 5 children, and then comma, and then the number of successes, probability of success for each trial, and that ended up being 0.25. And that creates this binomial distribution. You can see some dots here. I'll hit the I'll hit the magnifying glass. And these dots represent the probabilities of the outcomes. 0 successes, 1 success, 2 successes, 3, 4, and 5 successes. If we choose this little arrow here for cumulative probability, we get the ability, like we do with normal, to create some boundaries. If we want, for example, the probability of exactly 3 successes, then we might just say, I want the probability of X being between 3 and 3. And there is the point 0.088 being calculated. Let me put that on the sheet. Okay, 0.88. And if we look back at our notes, that's the same number that we had. All right. Probably that's probably exactly. Now, if we want greater than 3, we can just change this greater than 3. Well, the smallest number is 4, and the largest number is 5. And then we would have something like, yeah, there's about a 1.6% chance, okay, of having exactly 4 or 5 type of blood kids. And you'll notice that in, is still the same probability that we calculated by hand. All right. And so we can use this in order to go back and do this really long problem. Okay, remember in this problem, X was binomial with 10 trials and a 1/5 probability of success on any individual trial. All right, so let's change this to 10 trials. We can put a fraction in here, or we can put 0.2, and we want 6 or more, which means going from 6 to 10. And as you can see, the probabilities there are really, really small, and the sums of those probabilities is really, really small. Okay, we end up getting, for that probability that X is greater than or equal to 6, we get a 0.006 probability. And again, because the probability is less than 0.05, we would be surprised at getting six or more correct. Right? And that's using the calculator to do those calculations. Again, the command was binomial distribution, parenthesis, N for the number of trials, and P for the probability of success for each trial. All right.